Welcome to the CICS Symposium. I am Ina Ferrero, an assistant professor at CICS, here to give an overview of the Information Fusion Lab. The Information Fusion Lab is focused on machine learning for multimodal data, including methods that support a wide range of biomedical applications. Over the last 2 decades, we've seen a sharp increase in data abundance, opening new possibilities for the training of machine learning models, both in terms of variety and scale. In the area of health, specifically, electronic health records are widely collected and increasingly made public. Smartphones and wearables have become ubiquitous, leading to a democratization of data collection. This has led to a surge in multimodal data that's noisy and non-uniform. These datasets are collected across multiple populations and institutions at an unprecedented scale. Over the years, we've seen powerful specialized techniques that have been designed to handle distinct data types such as images, time series, and videos. However, comparatively less effort has been allocated to approaches that can address multimodal heterogeneous data collected in a non-uniform manner across multiple sources, despite its prevalence in real-world settings and its potential to improve prediction over single-source models. We'd like to find ways to integrate these many different types of data, as well as make them more accessible to users. All in all, the aim of our lab is to build hybrid systems that integrate multimodal, multi-source data and learn models that aid users interpret this data. Our research includes a wide variety of topics. Deep learning for the fusion of multi-resolution time series, images, and structured information. The incorporation of domain knowledge, or saliency in images, and the integration of multiple views for MRI analysis. Most recently, we introduced new models for normalizing flows and transfer of causal models. We apply our methodology to enable the early forecasting of Alzheimer's disease, the detection of heart anomalies, and the prevention of accidents in self-driving cars. In so doing, we are advancing the objective of CICS to use data science for the common good. We have a diverse team of award-winning Ph.D. students. In the next part of the video, they will present some of the research they have been doing in the lab. Thank you for your continued attention.
Hi, I'm Ke Xiao, second-year PhD student in the Information Fusion Lab. My research area is machine learning on medical imaging, mainly with cardiac MRI datasets, including weak supervision, computer vision, and segmentation. I worked on various computer vision projects using cardiac MRI datasets. Ina and I started working on the detection of bicuspid aortic valve disease at Stanford, and have continued this work now that I have started my PhD at UMass. Most recently, we have been working on the detection of mitral regurgitation and several image segmentation problems. Normal aortic valve has 3 cuspids, and due to congenital condition and unhealthy lifestyles, it could lead to a malformation of bicuspid valve. And if left undetected and untreated, it could lead to cardiac arrest or worse. The main difficulty in this project is that the condition has a prevalence of less than 2% in general population and only about 6% in our dataset. On top of this, we are working with unlabeled datasets from the UK Biobank. Here are some examples of tricuspid aortic valve and bicuspid aortic valve MR data. And this is the model pipeline where we apply domain knowledge on processed segments to form noisy, weak labels, which is in turn used to train a deep neural network model to generate the final predictions. In the final classification results, we have a 61% improvement in F1 score and a 171% improvement in precision. And model improves even further as we add more unlabeled data. In the t-SNE plot, we can see a clear separation, and even those misclassified cases look very similar to the BAV cases due to reasons like image quality and mild conditions. In the survival analysis we conducted, our predictions are corroborated with the findings. Our next project is the mitral valve regurgitation project. The mitral valve is the valve connecting the left atrium and the left ventricle of the heart. Mitral valve regurgitation is the condition where the blood flows back from the left ventricle into the left atrium. And if left undetected and untreated, it will lead to severe complications, including pulmonary edema, blood clots, stroke, heart failure. Here are some examples of the positive and negative mitral regurgitation cases in the 4-chamber view and 2-chamber view of the MRI data. And this is the model pipeline where we apply the masks generated from a segmentation model to the MRI, which is then used to train a deep neural network model. This is the pulmonary artery and aorta segmentation model I worked on. Segmentation is a useful method often employed to focus on the part of the image which is useful of the task at hand. In this project, I used methods like Hoff transform, watershed segmentation to segment the ascending, descending aorta and the pulmonary artery. And finally, this is the 4-chamber view segmentation I worked on. Thanks.
Hi, I'm Sidong Zhang, a first-year PhD student in the InfoFusion lab, and I will talk about Project Forethought. The objective of Project Forethought is the detection of Alzheimer's disease at least 2 years before symptom onset. To achieve this goal, we are applying deep learning models to multi-modal patient data, including brain magnetic resonance images. Alzheimer's disease is a condition that causes brain degeneration and, as a consequence, cognitive decline. Alzheimer's is irreversible. So far, every clinical trial for a cure has failed. The best chance of combating Alzheimer's is to detect early pathological changes in the brain prior to the onset of mild cognitive impairment. This makes it possible to conduct clinical trials on pre-Alzheimer's cohorts and paving the way to preventative treatment. We train forecasting models on the full multi-modal dataset provided by the Alzheimer's Disease Neuroimaging Initiative. The study includes subjects that show signs of cognitive impairment and Alzheimer's, as well as healthy controls. Multi-modal data, including brain MRI scans, cognitive test scores, and biomarkers, are collected from subjects over multiple visits, spaced 3 to 6 months apart. We believe deep learning models can identify potential pathological changes in the multi-modal data, thereby forecasting Alzheimer's onset. The video shows an example of brain MRI representing different cross-sections of the brain, scanned from top to bottom. Here we show how the degenerative process affects one slice of the brain. The subject transits from cognitive normal to mild cognitive impairment to Alzheimer's disease over the course of the study. We expect the model can learn from the multi-modal trajectory of patients and generate informative features that indicate the patient's status in 2 years' time. Our current model is called FLAIR. The trajectory data are first encoded to feature space F, representing the subject's health state. Then we use time series models to forecast the future health state F hat, and from the health state F hat, we obtain the future disease label Y hat. The model is trained by minimizing the trajectory prediction loss and disease forecasting loss. The trajectory prediction loss is a difference between the predicted next health state in the trajectory F sub VI hat and the actual next health state F sub VI. The forecasting loss is a common cross-entropy loss on the predicted label Y hat and the actual disease label Y, tau visits in the future. Our current results shows that the model working on demographic information and cognitive test scores together can reach an average score of 0.82 in the 18-month forecasting task, which is a considerable improvement over the baseline. That brings us closer to our goal of detecting Alzheimer's at least 2 years before symptom onset, opening the door for clinical trials of preventative drugs. Thanks.
Thank you for listening to that presentation on the medical imaging projects ongoing within the Information Fusion Lab. Our full video in the symposium showcase contains overviews of 2 more projects. One project is on applying deep saliency to pedestrian detection. The other is a more theoretical project on changing dimensions in normalizing flows. Do check out some of our other projects, which include handling multi-resolution time series and incorporating clinical notes. Their descriptions are up on our lab website. Please feel free to reach out during the symposium's Q&A sessions or asynchronously via email or Twitter. Thank you for listening and enjoy the rest of the symposium.